In 4.3, we looked at a shortcut for proving that two triangles were congruent. Now we're going to look at some more shortcuts. So there are other ways that we can prove that two triangles are congruent without showing that every single set of corresponding angles are congruent and without showing that every single set of corresponding sides are congruent. So in order to do this, we need to talk about what it means for an angle to be an included angle. So if we have two sides of a triangle, so say we take these two pencils as two sides of a triangle, and then we don't really care about the third side. But if we're looking at these two sides here, the angle between them is called the angle that's included between those two sides. So that's what an included angle is. All right, so we're going to use that for the side angle side congruence postulate. So what this says is that if you have two sets of sides congruent, so here's one set, here's another set of congruent sides, and you also have the included angle between those two sides as being congruent, that is enough to show that the entire triangle is congruent to the other one. So we don't actually need to find that these two sides are congruent to each other. We don't need to find anything about these angles. If we have this set of sides and this set of sides and then the included angle between them, that will force everything else in the triangle to be congruent as well. So if we have all of that, then we can say that triangle RST is congruent to triangle UVW. All right, let's use this in a proof. So we were given two pieces to this given statement. We are given that segment BC is congruent to segment DA. That's one of our givens. And then we were also given that segment BC is parallel to segment AD. And that was given as well. Now again, anytime we're doing a proof, what we want to end with is what we're actually trying to prove. We're trying to prove that this triangle is congruent to this triangle, so I'm going to write that down as our goal of what we're trying to get to. Okay, on the picture, it's already marked what we have, so we've got BC marked congruent to AD, that's what these marks here mean. And then we've also got marked that BC is parallel to AD. All right, let's look at angles. So, well, actually, first let's look at sides. So we've got that segment AC is shared between the two triangles. Both triangles have this segment. So we could say that segment AC is congruent to segment AC. So that's that one, and that's by the reflexive property, which I will abbreviate PROP. Now, if we're using the side angle side congruence postulate to prove that these two triangles are congruent to each other, we need to then use the included angle between these two sides. So that for this triangle is going to be this side right here. And then for this triangle, the included angle between these two sides is this angle right here. So we need to prove that those two angles are congruent to each other. Well, if we look at the fact that AD is parallel to BC, then we can look at this as a transversal cutting through those two parallel lines. And if we have a transversal cutting through two parallel lines, we know that alternate interior angles are congruent to each other. So that will tell us that these two angles must be congruent to each other. So we can then say that angle BCA is congruent to angle DAC. And again, that's because alternate interior angles are congruent. I'm going to abbreviate that ALT for alternate, INT for interior, and then angles. So alternate interior angles are congruent. Well, now we have enough information to say that these two are congruent. So we've got a set of sides congruent there. We've got an angle congruent there, a set of angles, and then another set of sides congruent there. So we've got two sides and the included angle, so that's side angle side. And so we can say that the two triangles are congruent by the side angle side congruence postulate. In example 2, we were given that these two, QS and RP, pass through the center of the circle. And so we want to know what we can conclude about these two triangles. Well, if these two pass through the center of the circle, That means that SM is a radius of the circle, so is RM, so is MP, so is MQ. All of those are radii, and every radius of a circle is congruent to every other radius of a circle. So those 4 segments are going to be congruent to each other. Now we also have a set of vertical angles here. So this angle is congruent to this angle because they are vertical angles. And so we've got side angle, side congruence. So we've got a pair of sides here, a pair of sides here, and the included angles are congruent. And so we can say that these 2 triangles are congruent. So we could say triangle MRS is congruent to triangle MPQ. Now there is a congruence that is tempting to try to use as a congruence, and this is side-side angle. This is very tempting to try to say that this is a congruence, but it is not. And so let's talk about what that would look like. So first of all, you might have, say, 2 triangles, and you would say, okay, so we've got this angle congruent to that angle, this side congruent to that side, and this side congruent to that side, and so that makes the 2 triangles congruent. Well, that is actually not enough information to say that these are congruent. So if that is angle we're talking about, so if we've got 2 sides in an angle, that seems like it should be like side angle side, like we just looked at. But if that angle is not included between the 2 sides, then that is not enough information to say that these are congruent. So you have to watch out for this. So let's look at how this works a little bit. So this is an example of 2 triangles that have these angles congruent, these sides congruent, and these sides congruent, but they are different triangles. So I've got something here that can help visualize this. So this angle is locked. I've got these pieces of paper taped together, so this angle does not move. This angle can move, though, up here. So I can swing this around. And then this side length is locked, and this side length is locked. So this is this angle, this side length, and then this side I can move around, but it will always be this long. So I can match up this over here and make this triangle ABC. Or if I take this side length and keep it the same length, but I start swinging it around, now you can see right now it's going past this segment, but if I swing it around to where it matches back up, so right there, then I get a different triangle with the same angle, the same side length here, and the same side length here. So depending on whether I have this side matching up over here, or swinging around and have it matching up over here, I can get 2 different triangles from this. So side-side angle is not a congruence. So we cannot use side-side angle. Now, there is an easy way to remember which one of these is not actually a congruence. So if you take these letters and switch them around, reverse the order of them, you get a naughty word that you're not supposed to say. And so that's a good way to remember which one is not the one that is a congruence. So the square is not a congruence. That is the only one that is not. All right, we actually do get a congruence, though, if this angle here is a right angle. So if this is a right triangle, then the 2 pieces of the triangle, the 2 segments that make the right angle, we call those the legs. And then the third side that's not one of the legs, that's not attached to the right angle, that side is called the hypotenuse. So then in theorem 4.5, this is angle side-side congruence, or side-side angle congruence, depending on how you want to say it. So we've got this angle congruent to this angle, this side congruent to this side, and this side congruent to this side. But if this is a right angle, then we can actually say that these 2 are congruent to each other. So if in a right triangle we have a hypotenuse and leg of one triangle congruent to the hypotenuse and leg of a second triangle, then the 2 triangles must be congruent to each other. So here I can say that triangle ABC is congruent to triangle DEF. Let's use this in example 3. So we're going to start with what we're given. Now in this one it doesn't say we're given anything, but we can look on the picture. So anything that's drawn on the picture we can use as part of our givens. So we can say that segment AC is congruent to segment BD because we're told that those are congruent based on the picture. And so I could say this is given to us because it's marked on the picture. I can also say that angle ABC and angle DCE are right angles. And that's given as well. So it's marked on the picture. These two angles are marked as right angles. Okay, so if we're going to prove that these two triangles are congruent by a hypotenuse leg, that means we need to show first that they are right triangles, second that they have a set of hypotenuses congruent, and third that they have a set of legs congruent. So we need those three pieces of information. We have to prove they're right triangles, we have to prove that they have a set of hypotenuses congruent, and a set of legs congruent. So let's start with the fact that they're right triangles. Well, if these two are right angles, that means that the triangles are going to be right triangles. So if you go back to the definition of a right triangle, it's a triangle that has a right angle in it. And so we can say then that triangle ABC and triangle DCB are right triangles. And the reason we can say that that's true is because that's what it means for triangles to be right triangles. So the definition of right triangles tells us that if we have right angles in the triangle, then it's a right triangle. All right, then let's try to get the legs. So the legs, if we look at that, that's going to be AB and CD. Well, we don't have any way of proving that that set of legs is congruent. However, they share this leg here, BC. That is a leg on both triangles. And so we can say that that's congruent to itself by the reflexive property. So segment BC is congruent to segment BC. And we've already got the hypotenuses. That was given to us. That's statement 1 here. So segment AC being congruent to segment BD, those are the hypotenuses of the two triangles. And we were told that they are congruent based on the picture. So we now have enough information to say that the two triangles are congruent. So we can say triangle ABC is congruent to triangle DBC. I'm sorry, actually that should be triangle DCB. And the reason that we know that's true is hypotenuse leg. So again, what we did here is we showed that they were right triangles because these are right angles. We showed that we have a set of hypotenuses congruent because that was actually given to us on the picture. And then we showed that this set of legs, where we have it shared between the two triangles, so BC is on both triangles, and since a segment is congruent to itself, we can say that this set of legs is congruent because they're the same segment, because the triangles share them. So that gives us the fact that they are right triangles. It gives us the fact that they have a hypotenuse. The hypotenuse is congruent and a set of legs congruent. So that means that the triangles themselves must be congruent to each other.